Welcome to workshop of Beyond Logistic Regression in R. My name is Siavash Jalal. I'm part of UCLA Office of Advanced Research and Computing. Our statistical method and data analysis group in that department. For now, 4 people working in this group. My supervisor, Andy Lee, also is here. If you have any questions related to the workshop, you can ask questions in the chat. The page of the workshop is here. I'm going to send it one more time in the chat for people who just joined. You can click on this page. You go to the page that you are seeing in the screen. You can click on this link to get to the slides of the workshop. And our codes are here. There are these codes also for you if you like to participate in exercises. So in order to download the code, you can right click and save link as, and save somewhere in your computer, in your desktop, perhaps, or you can click on it and then copy the whole thing and paste it into R. Right click, save link as, and it's saved as R code. Also, you can save this one. So with that, I'm going to start. There are some exercises we go together. I give you some time to think about the exercise and run it. It's very easy. And at the time, we go over that. But for now, I start with these slides, okay? If you have any question related to the workshop, you can send it in the chat, or you can, I think we are not a big group, so you can, if you think your question is very relevant, you can go ahead and share with everybody, right? Okay. So the workshop, I start with some introduction and some review of the knowledge you already know probably, but is related to this workshop. So I'm going to start with saying what we want to do in this workshop. Basically, this workshop, we want to extend our knowledge about logistic regression with multinomial and ordinal logistic regression, with some examples in R. Let's say the regression analysis in general is a statistical tool to explain relationship between a dependent variable and some or one independent variable or some independent variable. As you know that in linear regression analysis, in linear regression, we assume this relationship can be explained in a way in linear form, okay? However, if the outcome variable is continuous variable, we can use ordinary least square, as you already know, to estimate the coefficient of the model. For now, I'm not going to go to detail, just as definitions. Ordinary linear square or least square, ordinary least square, have some assumption. So those assumptions to give you a good estimation of the model, which specifically defined a estimation that is unbiased with lowest sampling variance. For that, the errors have mean equal to 0. Errors are independent, and error have equal or constant variance, and this calls homoscedasticity or homogeneity of variance. The error is the unexplained part of the model that cannot be explained by the linear model. Another assumption we have for ordinary least square that people think is very important, but it's not really, it's not necessarily that ordinary least square to give you an unbiased with the lowest variance. Is that the errors follow a normal distribution. Okay, so this assumption also help us for when we want to talk about it, test statistics and things like that. So we can run the model using maximum likelihood, estimate the coefficient, and that maximum likelihood estimation now is the same as OLS. Okay, so if there is a lot of things that we haven't started yet, so we will go, and if your question is relevant to that part, you can ask it again. Now, the purpose of this workshop is when the outcome is not continuous, right? Is a categorical value. A categorical random variable is a variable that takes a limited number of possible values with some underlying quantitative variables. Okay, so this categorical variable could be nominal when there is no rank between the categories. For example, blood type, gender, race, zip code. These are examples of nominal categorical random variable. Ordinal variable is a categorical random variable or categorical variable when you have a natural order, right? If you can establish some ordering between this category, then we call it ordered or ordinal variable. Most likely, the distance between this order are not the same. So it could be, but most likely the distance between lowest level and middle level and highest level are unknown. Okay. So example of ordered is when the response to a survey is strongly agree, disagree, agree, and strongly disagree, right? So I said it not in order, but is ordered from strongly disagree to strongly agree. Notice that the difference between a strongly agree and agree can be different than agree to disagree and different than disagree to strongly disagree. However, if this difference of distance is very large, later we have some assumption in ordered logistic regression, which it called proportional odd assumption, and we get to that. If the distance is very different, then most likely we violate that assumption. But that assumption is not the distance between the ordered categorical variable as outcome. It's about the predictor. We will talk about that assumption later. So in ordered categorical variable, we cannot quantify how much bigger or smaller. If you have 1, 2, 3, 4 level here, for example, then probably you can use a numerical random variable from 1 to 4 and run the model using OLS model as a continuous outcome. So, but usually that distance are not, if that's if you cannot have the same distance, then it doesn't make sense to run the model as a continuous with numerical number. So another example is that social economy status can be categorized as low, middle, and high. If the categorical variable have only two levels, then we call it binomial random variable. For example, in Philippine coin, we can have only head or tail, right? So only two options. Or a medical test can have only two possible outcomes, as positive or negative. Or smoking is a binary with yes or no. So it doesn't matter to treat this binomial thing as ordinal or nominal. It doesn't matter because you only have two levels. Now, as previously to this beyond logistic regression workshop, we know that if the outcome variable is binary, we can run it as a logistic regression. But if the outcome variable is multinomial but nominal, then we can run a multinomial logistic regression. And if there is order in the outcome, we can run it as ordinal logistic regression. Now you see that there is a logistic in all these three different type of regression model. That logistics comes from a logistic function that use as a link function to transform a linear combination of the coefficients or the predictor or predictors and transfer that prediction to a probability. That value is between negative, could be between negative infinity and infinity. But if you look at these three different type of logistic regression, there is a probability for each outcome. So that the name logistic comes from this link function. We call it logit function. Usually when you read the data, a variable that is categorical is read as a character variable. So I just create this fake data X as a character variable of A, B, C, D. And as you see, you can print the data using just, this is C is combine all these values into a vector. And then I print it by typing just X. And then I get the ABCD. The class is character, right? Now, I know this is not a character, this is a categorical random variable, and I want to use that in the workshop or in analysis. Then I use a function factor to transform X to a factor variable. So XF is now a factor variable with these levels and these labels. By the way, I didn't need to put these levels and these labels. In R, by default, the levels is going to be all the unique values sorted, unique value of the variable as character, sorted from low to high or ascending order. So it depends. If it's letter, start with letter, is going from A to Z. And if it's number, then it goes from 1 to, for example, 3 or 4. Okay. So you already ordered this way, and the label is going to be the same as labels. I will go for exercise in RStudio that I can show you that these levels there is under in R, it keeps a value from 1 to 1, 2, 3 to the number of category that we have, and assign which one is the first as 1 and which one is the last as the highest value. We will see that when I go to R. If we run levels, we get the levels of that variable in order. So here the level was A, B, C, D, but I can re-level and change the reference level, which is in data analysis important sometimes, especially in regression model, to another level. So now by re-leveling and making the reference to B, I change the reference of XF to be B. But I haven't saved it anywhere, right? I didn't assign it. So this doesn't change the actual XF. So if I want to save it somewhere, I have to assign back to XF or to another variable. So now XF is ABCD, same, but levels is going to be BACD. This part is when you want to combine the levels to one level, because I put this as optional to see how the workshop goes. You can check that, but it's not relevant much in the workshop, but this is good if you want to combine levels to one level, but I'm not going to I'm not going to spend time on that. You can take a look at that. Ordered factor, because we are going to later use ordinal logistic regression. You can make a factor order in R. So the code is the same factor, but there is option that I by default is false. That's why I didn't use it before. Make it to true. So if you make this order to true, then the result is going to be order factor. So I call it x.of as order factor, and or I can run ordered, which is the same code as factor with order. So ordered is another way to order a variable as factor. So if you look at this result, you can see still you have the same thing as a factor, but the levels are in order. You see A is less than B, is less than C, is less than D. That means they are in order. We can change the order. If we want to change the order, we can re-specify the levels in different order. So if I use the same, this x.of was ordered factor, right? I'm going to use that as input with different level, and now I change the order from D to be a smaller, and then B and C and A, right? From highest to lowest, you can think of it. But the value doesn't change. The value is still A, B, C, D. Value X or F. The fact that object is not going to change. We just change the order. We can also change the label of ordered factor or any factor variable by adding label with different label as we defined. So here I wanted to define A to be a strong disagree, B to be disagree, C to be agree, and D to be a strongly agree. So I can just label them and run as ordered XF with label, and then it's going to be labeled, right? So if I print this. You see the parentheses I put over the whole code, it prints the result at the end. It runs that and it prints this XOF. And you can see A now is a strongly disagree, B is disagree, C is agree, and D is a strongly agree. And the levels is going to be the same, right? In this order that I defined because already the order was this, right? I haven't changed this to be this order, so it's not going to be different, right? Okay, I just changed the order now. Or I can use that factor and I change the levels to be different. Oh, okay, sorry about that. No, this is another thing, another person. If I want to change the order, before was from a strongly agree to a strongly, from a strongly disagree to a strongly agree. Now, if I want to change the order from a strongly agree to a strongly disagree, so this be the lowest order and this be highest order, then I have to change the levels here. So if you change the label, it's going to change the data. So I have to change the levels. So as you see, the data is the same, right? Still, A was a strongly disagree. Now A is a strongly disagree. And then this B was disagree. And by the way, if you want the slide, don't go advanced, you can click on K. So then it doesn't advance with the mouse. So that's a good idea if you want to copy paste the code and run it in R. So as you see now, the order is from a strongly agree lowest to a strongly disagree highest, right? Instead of this way. So this is basically some overview about factor variable in R. And here it says the second line, you don't have to say order true because it's already ordered here. So next, let's now look at the data as we see in our data analysis and see how we can change variable within a data set to be factor, right? So the data set that I'm going to use in this workshop is HSP data. There is another data set later I'm going to use for order logistic. Okay. The data is HSP demo data that there is a lots of example in our page use this data set. So I read the data using read.csv because the data is in CSV format. And the default works with this data, so I don't have to check because it's the default of read CSV is comma separated. So I don't need to do, and header is true. So you don't really need to do any other option here for reading this data set. This is a way to read the CSV file in R. The names of data set are here, the names of variables. So I have 8, 9, 10, 11, 12, 13 variable. ID is ID of a student. As you see, because it's a number, when you read it, it reads as integer. So you can change it to character if you like. But that's not, we are not working with this ID, so we don't care about that. Variable female is a character, and the character are female and male, right? So wait a second. I think when you read the data, it's not going to be female and male, but I need to check later. And then variable social economy status also is character. As you see, is low, middle, high, and low again. So it's low, middle, and high, 3 levels. There is there is a school type, is public or private. There is a variable program, which says what type of program students are going to enroll in their school. Is going to be vocational, general, and academic. There are variables, continuous variable about their performance, read, write, math, and science, and social sciences score. There are whether or not a student in honor program, enrolled or not enrolled, and then there is award, number of award stuff. I believe when I read the data is not reading that correctly, but we will check. So now I'm going to switch to R, and I'm going to change these variable, which are as character, to be factor variable. So with that, I'm going to switch here. Let me just make it the font a little bigger. So I think now is better. Clear this. Okay. So let me clear this environment first. So because I run the code already. So in this workshop, I'm going to use some packages. I will still load those packages when I use that. But however, you can load all the packages at the beginning. In the email I sent to you, I said, if you haven't installed those packages, it's a good time now to install them. But it takes time, so I'm not going to wait for you. So hopefully you already installed those packages. But if you haven't installed, you can run this code and install the packages. I'm going to keep it like that. So, okay. Install packages, command dependency is true, right? So I'm going to load these packages. When you start the R at the first time, you don't see these packages in the R. So you need to run them. So the package that, I already have a lots of packages already loaded, but I'm not going to close my R and open it again, but it's there. But anyways, this is the packages that we use in this workshop. We can read the data, and that what I was curious. So yeah, these variables are character. I thought there are number 0, 1, but this is correct. This is the way that we see the variables. Now I'm going to make the variable female factor. So by using factor, I'm going to make female factor. And if you check the level of female, is female and then male. If you want to change these levels, I can get the table of this factor. It gives you the number of observation in each level. Okay, by the way, let me just make this change it to here, or maybe I should change it to this panel. And then I can relevel, make the male to be reference, because we call this variable female. It's nice to compare female to the reference group. So I'm making male as the reference group. And now if you look at the levels, it's going to be male, then female, right? In the workshop page, this part is exercise. It says in HSP data, transform variable, a school type program, honors, and social economy status to as on order. So social economy status is low, middle, and high. For now, just make them as nominal. Don't make it as order. And proportions of each category, you get that. So I'm going to wait a little bit for you to run this code by yourself, and then I'm going to run it. Okay. And meanwhile, if you have any question, you can ask. So, Andy, do we have any specific question that I can explain or no?
Not particularly right now, no.
Okay. Okay. So I continue. I will go over this exercise quick because we have a lot of content that we want to cover. So basically, using factor, you can run it and then makes a school type factor, get the table, right? This is easy. I just make this variable here and make it as factor and run it. So program factor and the table. The table is going to be the same order as the levels. So if I type levels, HSB prog, then I get the same order as you see in the table. So the order of factor plays a role when you plot it, when you make a table and things like that, or when you run the regression model. What else? Honors, and then social economy status as low, middle, high, right? Because before I think was different order, so I want to make the order to be in this level. But still, I didn't make it as ordered factor. And then you get the proportion. Now, variable honors, let's do that. Reference of variable honors, change it to not enrolled as reference group. So read levels, I think read level, and then was HSB $ honors and reference, right? That was the option equal to. Now you can put not enrolled. Before that, let me show you what was the reference. So this was enrolled was the reference, the first one, because E comes before N, right? So now we want to make it not enrolled as reference. So now if I do levels of HSB $, if you want to get one column of a data frame, you do $, you can use $. So now is not enrolled and then enrolled. Okay. So the second exercise is going to be multinomial. We will go over that later. Okay. So that was about factor, and we did it with the real data. So this is a good exercise to first make sure to fix those variables in the data as later we want to use in analysis. Another thing, another suggestion that I see a lot of people do that. They run a bunch like 1,000 data cleaning line, and then they get to the data set that they use in their analysis, But what they are doing is they don't save this final data set. It's very important to save this final data set. So every time you want to run the analysis, you don't have to run all those data cleaning. Okay, so next slide, I'm going to go over some important aspect of this logistic regression, multinomial logistic or ordinal. They are all related to these definitions. First is odds versus probability. What is the odds? The odd is fraction of probability divided by 1 minus probability. So basically, it's probability of some event happening divided by probability of that event not happening, right? So this is defined as when you have a binary variable most of the time, but we will extend that to the more cases. So let's say probability of a student enrolling in honor program on average is 0.3, right? Then we can define or calculate probability of the odds of enroll as 0.3 divided by 1 minus 0.3, which is 0.428, right? This is the odd, right? And also we can calculate odds of not enroll, right? The event of interest now is not enroll. So you divide it by 1 minus probability of that event. So it's going to be 0.7 divided by 1 minus 0.7. Now you see this number is not between 0 and 1, right? This number still is, but the odd is always a positive number. Okay, it cannot be negative number. And could be very large number, right? Because I can make the denominator as small as I want, right? So I can make this very small. So the whole thing is going to be very large. The inverse function of odd transform the odd back to probability. So I can solve this equation for probability, and then I get the probability, which is odds divided by 1 plus odds. So I can easily calculate probability from odds, right? I'm not going to spend a lot of time. I just wanted to tell you that there is a way to get the probability from odds, right? Because solving this, you have one unknown, and we can completely solve this. So if the odd is 2, then the probability is going to be 0.67. For a categorical random variable with multiple category, more than 2, we can extend this definition of odds by odds of an event, the probability of an event to probability of a reference event. For example, in variable program, we can divide probability of general. So program had 3 levels: academic, general, vocational, right? And, let's say academic is our reference group. I can divide probability of general by academic to get odds of general versus academic. So I cannot say odds of general, because odds of general is going to be probability of general versus not general. But here I'm calculating probability of general versus another level probability. So it's going to be probability of general divided by probability of academic. So in our data, if we get the proportion for each category of program, we can calculate odds of general versus academic and odds of vocation versus academic. So odds of general versus academic is this probability divided by this probability, right? So it's not this probability divided by 1 minus this. It's odds of general again versus academic. In this workshop, actually, I like to use the generalized odds, but in literature and books, people simply use odds, but they say like odds of this level versus the other level, right? They don't say general odds of this level versus the other level. So odds of two events versus each other. And they calculate odds of vocational versus academic again, right? And I get 0.47. So looking at this 0.47, you can say, you can feel that it's close to 0.5, right? So that means basically the probability of vocational is half of probability of academic, right? So it's good to get a sense of what odds really means. This part also, as we did here, that we calculate the probability of odds. We get the probability from odds. If we have all odds of all levels versus a reference level, we can calculate all the probabilities. And the calculation is here. So there is a lot of little math, right? It's not one equation only, but you can solve that and get the probability of all levels, which is used in multinomial logistic regression, but I'm not going to go over that. We are using software and that software gives us the predicted probability. So now, after we understand odds, now another thing comes handy is odds ratio, right? Odds ratio is the ratio of two odds. Basically, odds itself was ratio of probabilities, right? Odds ratio is ratio of probability, right? So each of the nominator and denominator is itself is a ratio of probabilities, right? So odds ratio is odds ratio of one event for one group versus the other group. When we talk about odds ratio, we want to compare odds of one group versus another group. So that's why I say odds of enrolled, right, for honor program, given female for females, group of female, and for male, right? So divided by the odds for male. So it's still odds of enrolled, right? You see, it's still odds of the same event, but comparing between two groups. So basically that is odds ratio. Okay. I will go over that exponential things like that, but very quick, right? Just be patient a little bit. So to get that odds ratio, I can get the tabulate of enroll versus not enroll for male group and female group. So I get a 2x2 table, right? Please, if you don't have any question, please mute yourself. Thank you. So I get these 2x2, and then I can run the proportion table to get the proportion for margin 2. So I want by column margin, right? That's why I put margin 2. So I want to get proportion for male and proportion for female. So I want to calculate these odds for female group divided by the odds for male group. So by doing that, I can calculate the odds of enrolled for female, right? So this value divided by this value. So it's probability of female, probability of enrolled given female divided by probability of not enrolled given female, right? This divided by probability of enrolled for male divided by probability of not enrolled for male, and that gives me the odds ratio of female, odds ratio of enrolled for female versus male, right? So it's basically we can by this value we can talk about, we can compare these two odds, right? Odds of male and females, odds of enrolled for females and males, right? It's a little confusing, but however, that number tells us that the odds of enrollment in honor program for female student is almost twice, is about 2 times of male student for male student, or odds of enroll for male students, right? Or we can do a little math and get this value -1. So it's going to be about 92.92 times 100. Then we can say odds of enrollment for female student is about 92% more than male student, right? So is either this times male or this percentage more than, right? So you can use either way. And you can see that we use this type of explanation of the coefficient when we do logistic regression, right? So we didn't have to do this proportion. We could just use the frequency table to get the odds. I'm not, again, so it's going to be 34 because, because we calculating the odds is the ratio of probabilities, and in the probability you have the denominator that is the same, and we cancel, right? Basically, those denominator is total number of male and total number of female. So we can do that to get the odds ratio. Now, there is something that I wrote here. It's important. If we want to calculate probability of one group from odds ratio, is only possible if you have probability of other, the odds of other, right? So if, from odds, you can calculate probability, right? If you want to calculate probability from odds ratio, you have to know at least one of the odds to get the other odds, and then to get the probability. So this is important things that people don't notice sometimes. And that's why when they run logistic regression, they try to explain the coefficient as a risk ratio, which is not possible, right? Is odds ratio. So, okay. So that's exactly the answer. So, people want to explain the result based on risk ratio, is not. But relative risk ratio is the same as odds ratio, okay? Relative risk, okay? And that name comes in multinomial variable. In multinomial variable, we can extend this odds ratio as the odds of a group versus reference group comparing between two groups, right? So the outcome is whether they are in general or vocational or academic. And you want to compare odds ratio of these events comparing between these two groups, right? So that's why you use given females. So the odds ratio or general odds ratio defined as odds of some event versus reference events for one group versus divided by odds of the same event compared to reference events for another group, right? So basically this formula defined as odds ratio of general versus academic for female to male. Okay. So this is kind of extension of odds ratio when we have only binary variable. So you need to think about this odds ratio a little more to understand what that means basically, but I do one example here. Let's say we have the program and we want to compare the odds ratio of each level versus reference level for different groups, right? And then I can make a tabulate of program variable, which is academic, general, and vocation, versus the gender, which is male and female, right? The gender here is binary. So I get the all frequencies, right, for each level. Again, like go back to the proportion that we calculate proportion. I'm not going to calculate proportion here. I just want to use the frequency to get the odds ratio. So basically, I want probability of general, and the reference group, let's say, is academic, right? Is academic, as you see. So I want to divide to get the odds of general versus academic, I can just divide 21 divided by 47. And if I want to get the odds ratio of female versus male, I can divide 24 divided by 58 and then divided by 21 divided by 47. Okay. Or for vocation, I can do the same. I can divide 27 divided by 58 and then divide by 23 divided by 47, right? And then that way I get the odds ratio. So basically this number tells us the odds of general versus academic is for female is 0.96 times less than odds of general versus academic for male, right? So it's more likely for male to go to general program versus academic program than female. Okay. So, or if you want to, you can use percentage and do again, this -1 is going to be minus 0.074, and because it's negative, if you make it as a percentage, you have to say percentage less. So if you want to explain it in a percentage, you can say the odds of general versus academic for female student is 7.4% less than the odds of general versus academic for male student. Okay. So next slide, we are talking about logit function, logit link. Now, we understood the odds. Now, odds makes a probability, a value between 0 and 1 to a positive value. Now, how we can get that positive value to a value between negative infinity and infinity? So basically, if we want to do that, we use the log function. So basically, log function, I use this first, so it's more clear. We did odd to get the value from 0, 1 to a value from 0 to infinity. Now we use log function to make this log of odd to be a number between negative infinity and infinity. And then this function is called logit function. This is a link function between probability to a real number, which is possible that a linear prediction gives you. Okay, and I will talk about linear. That's why we use this logit function for this type of logistic regression, right? Because we have a category and then we want to get the probability of each category, right? We want to predict probability of each category. So, okay, now let's talk about binary logistic regression. Very quick. Again, these are all review and it's 2, so I have to be a little quicker. But these are important because it's the same kind of idea and the definition applies in multinomial and ordinal logistic regression. So now suppose we have a dependent variable which is binary. Oh no, first okay, let's talk about first linear regression. So if y is a outcome variable, we can have the linear prediction of all predictors this way to get that outcome variable. So basically, we can model y based on these predictors using this model, right? This part is the mean or expected part of this mu given these predictors. And there is some error, which is uncertainty of the model, right? This error that I talked about, the assumption in OLS is this, right? So basically, you can model it this way, right? So this is the mean of the y given specific values of predictors as a linear combination of those predictors. And there is an unexplained error term, right? Which assume to have mean equal to 0, right? That's why you get the mean of both sides. This part goes away, right? Now, this right-hand side is called the linear predictor of the mean, of the outcome, of the dependent variable, right? So this is for when you have a continuous random variable. In logistic regression, you have a continuous outcome, right? In logistic regression, we say that the log odds or log of probability of the outcome has linear relationship with predictors, or can be write as linear predictor, right? So if we take exponentiate of both sides, we get the odds equal to exponentiate function. Exponentiate function is inverse of the log. So that log we talk about was the natural log. Is number e, which is natural number, to the power of linear predictors. Or we can write it in mathematics, exponentiate of this. In our function exp does the exponentiation. Now we can, again, this is odds, right? We can use these odds and calculate predicted probability, which I don't go over that for now, right? But it's very easy calculation. If you're interested, you can see it. Okay, but what is important for us is that this equation, right? This one, right? Or this one. So 1.3 or 1.4. Okay. Logistic regression in R. So in R, we use a building function is already there. It's not a, is in package. I think it's package stat. It's GLM function that can run logistic regression using the option binomial, because the link for this function is going to be login. So because of the outcome is binary, we use a binomial distribution, and we use this link function to run this logistic regression. I don't have time to go over those like likelihood function and how we get the binomial, things like that. But if you look at the help of GLM, you will see the formula is like this, and there are some options. We are not going to go to this option. We use the logistic regression as the very basic, but you need to have a formula to run a logistic regression. You need this part for sure for a GLM, and you need either data or everything in the formula should be already in the workspace as an object. So if you have a data frame and you don't extract the variables, you have to have a data too. So in this workshop, as example, we run the logistic regression of honor as outcome and variable math and female as predictors. So run the logistic regression using GLM. Again, this is the formula, and you already know it does that the formula of regression. Here you have the outcome in the left side. You have this tilde, which is a key in the left upper of under ESC in your computer. And then you have math and female as predictors, separated by plus, right? Here I don't have interaction. So if I put multiply here or a star, then I included interaction to the model. And the data is HSP. The family is binomial, link is legit. And if I run this model, I extract it using summary, I get this result. Okay. The first is the call is the formula of the model and tells you what you're running. Then is deviance. It's kind of like a residuals, but they call it deviance residual. It's basically predicted probability minus observed value, which is 0 and 1. And it's summarized it here. And then you get the coefficients here. You get the intercept and the slope for each of those variables here. Because the female was a categorical variable, is a binary predictor. The reference group was male, so you see female here. So female is whatever is not reference. So if you don't see something here, that means that level is the reference. Math was continuous, so you get this value. And you get all other like a fit for fit, the null deviance and residual deviance, things like that. I'm not going to go over this definition of these things, but they use for model fit. And this model converges after 5 iterations, and you can get the coefficients also by using coef function of the summary, which gives you a standard error. It gives you basically this part, right? The intercept and those coefficients. So basically, if we want to write the model as formula 3.1.3, this is the model. This is the linear predictor, and this is the log of odd of in-row, right? So now if we want to interpret the result, we say that for 1 unit increase of math score, the log odds of enrolled increased by 0.18 on average, holding other predictors as constant, right? Or for female, for this value, you say that female have log odds of enrollment 1.1208 more than male, right? So, but again, I interpret those as log odds, right? So usually people don't know what log odds means, right? They don't have a sense of what that is. And then, okay, the slope. A slope is the log odds of enrollment for when the math is 0 and female is at reference group, or this one is 0. This female, it could be 1 and 0. 1 is when is female, 0 is when is male, right? So everything else is going to be 0, and then you end up with the slope. But usually it's not very useful to interpret this slope, log odds of this. This is a very, very small number because, you know, is in log metric. So because it's not very realistic that somebody has math score equal to 0. And that's why. So if I exponentiate this coefficient, then I can explain them as the odds ratio, which is more understandable for people if you want to write in your paper. So if I exponentiate this coefficient, I get this value. Basically now, and then you can do the confident, but okay, so something about the confidence interval of the coefficient. There is 2 ways to get the confidence interval of generalized linear model. One way is plus minus those standard errors, using just a standard error, or they call it sometimes vague confidence interval. Another way is to use the likelihood ratio and say where that likelihood ratio test rejected, and they call that profile confidence interval. So we see that later also in multinomial logistic and ordinal logistic. Okay, so I do exponentiate this confidence interval, and then also the 50, this 2.5 percentile and 97.5 lower and upper limit of confidence interval. Now everything is in odds ratio metric. So now I can say the intercept, which is very small, right? It's almost 0, is the expected odds of enrollment for a male student with math score equal to 0. So basically, the enrollment, chance of enrollment is almost 0 for if somebody has math score equal to 0, right? But because it's very outside of our data, then we don't really interpret that. The second one is the math. So for math, we can say that for 1 unit increase of math score, the odds of enrollment increases by 20%, right? This value -1 is 20%. So 1.2 minus 1 is 0.2 times 100 is 20. So we can say for 1 unit increase of math score, the odds of enrollment increases by 20%. Or increases by a factor of 1.2, whichever is easier. But here I will say that by the factor, because this value is like 300%. So I don't use the percentage to interpret that. I would say that the odds of enrollment for female is about 3 times more than male, holding other variable constant, right? So for holding other variable constant basically means that if you pick 2 people randomly, 1 male, 1 female, with same math score, then expected odds of enrollment for female student is 3 times more than that male student, that random picked up male student with the same score. You cannot compare a female and male, one with 100 score in a math, one with 50. That's not fair, right? So that's why this. And in this example, we don't have interaction. Basically, if I included interaction, then the effect of each of those would change if the other variable change. But here I restricted the interaction to be 0. Yeah, this was the logistic regression, basically. Now we are ready to go to multinomial logistic regression. Okay. It's 2:21. So hopefully I can finish it quick, and then we do example, and then we take a break. Okay. So in multinomial, we have multi-level. So capital J assumed to be how many levels of that outcome we have, right? And then for every small j from 1 to capital J minus 1 category, we can define the log odds of that category versus the capital J category as reference group, right? So before we talk about this this type of odds, right? Extended definition of odds as odds of one category versus the other category. Let's say J, capital J is our reference group. Now, Y being in a small j, odds of Y being a small j, to the given all these predictors, right, is the probability of Y being in that small j, given that predictors, to probability of Y being equal to the capital J, which is our reference group, given that predictors. And log of that odd is equal to linear predictor, right? Again, same thing as logistic regression, right? So this is, again, is a logic function, but in more general term. As you see here, for every small j, you have one equation, right? So you have one equation for j equal to 1. You have one predictor, linear predictor equation for another level. So you have, again, another set of that coefficients for every level other than the reference level. So if you add all the probabilities for all the levels, you should get 1, right? all odds of all probabilities. Then you can calculate probability of reference group as 1 minus probability of all other group that you calculate these odds from them, right? If we exponentiate both sides, you can write the formula, the model as exponentiate rate. So is probability of jth group divided, a small j group, divided by probability of capital J, which is the reference group, is equal to exponentiate of the linear predictor. Okay. As you see here, we have 1, 2, 2p plus 1 coefficient to estimate for each of those levels. So if we have an outcome for with 3 levels, then we have p plus 1 times 2 parameter to estimate. If we have outcome for with 4 levels, then we have p plus 1 times 3 coefficient to estimate, right? So let's say we have 10 predictors, then it's going 10 plus 1 times 3 is going to be 33 coefficient to estimate, right? If you have a data set of sample size 100, this model is not a good idea to estimate this model. We end up with the model break because of the you don't have enough observation for each of those levels for each of those conditions. That is in general calls the separation. So if you don't have enough data for each of those levels for all those conditions, then you end up to get odds equal to infinity. And that's why sometimes you cannot estimate those when you have a small sample size and you have too many levels of the output. So multinomial is not a good idea. Multinomial logistic regression running that is not a good idea to have a small sample size and many levels, right? So if you want to know more about this separation, quasi or complete separation, you can look at this link. You can click on that and they explain it in logistic regression model and how to deal with that. Another way is like Bayesian, but I'm not going to cover that in this workshop. Something that usually people forget to mention and to make sure that is correct is the irrelevant independence, assumption of independence of irrelevant alternative. What that means is that if you exclude or include another category to that multinomial variable outcome, then the relative all should stay the same, right? It shouldn't change. So adding another level to the model shouldn't change that relative odds. So the model shouldn't change. So that assumption is important, or maybe not, but if you want to know that how important is important, but can we test that? It's very hard. So I let you look at this page. Actually, it's from Paul Allison, and it explains this how relevant is independence of irrelevant alternative assumptions. So take a look at that. Anyways, so these two references for you to explore yourself. We don't have much time to go over those. So this part, I explain how you can calculate the predicted probability using odds. And again, like logistic regression, but it's a little more. You need to have all the odds. So now let's run our first multinomial logistic regression in R. So in this example, I'm going to run the variable program, academic general vocation, 3 level of that categorical variable. In this variable, academic is the reference group. So this is basically our capital J group in the formula that we had before, right? In the last page. So that academic is basically this category, right? And then these two groups, general and vocation, is J equal to 1 and J equal to 2, right? So it's two other groups. You can get the predicted probability. Basically, this is predicted probability for intercept only multinomial logistic regression. So, but we want to predict that predicted probability using a variable social economy status and a continuous variable right. So to do that, we use the package name NNet. There are several packages can run this multinomial logistic. But I'm going to use this package because it's easier to use, not is because it's the best package to use. So again, K is, so I use, there is a function multinom in this package, so you can run it. Again, like any LM or GLM, but here, because it's multinom, you don't have to say the family or the link. It's run based on link, logit, and family multinomial, right? Runs the model, store in M multinom, and after you run, you see some information that this model, it converge, it gives you the final log likelihood, negative log likelihood, and converge at the maximum likelihood point. And estimate using maximum likelihood, but it's a little more complicated. It's because the likelihood function is very complicated, so you cannot just take derivative to find the maximum value. So, and then you can get the summary. Okay, let's look at the summary. Again, we said we have 3 levels, so we have to have 2 set of coefficients, right? First, we see all the coefficients, right? Before in other regression, this was column-wise, but here is a row, right? This is the intercept for general versus reference group. This is the coefficient for social economy status had 3 levels, so it omits 1 level and compare other level to the reference level. And we have the coefficient for right. And then we get the standard errors of these estimated values. It doesn't give you Z value and P value. You have to compute that using this standard error and the estimated value. So this is the result of this. And now let's see how we can interpret this result. If you summarize this result, if I put it in a formula, I should have one formula for this intercept, and this is for social economy equal to middle, this is social economy status high, and this is right. And then I have to have another formula, right? Another equation. So these are 2 equations based on those outcomes, right? So I summarize those as the formula in equation 2.1, right? Log of odds of general versus academic is equal to this, and then log of odds of vocation versus academic is equal to this equation. So we have two equations. Now, if you want to interpret, let's say the intercept. This intercept is the log of odds of general versus academy when social economy is low and right is 0. Okay. And this value is log of odds of vocation versus academy when social economy is 0 and right is 0. Social economy is low and right is 0. Or we can say expected, because this is this model gives you expected odds of log of odds. And then for right, we can say for 1 unit increase in the right score, the log of odds of general versus academy decreases by this amount, decreases by 0.059 or approximately 0.058. And for 1 unit increases of right, the log of odds of vocation versus academy decreases by this amount, right? And so on and so forth. This is the comparing medial to low. This is the comparing log of odds of high to low. Keeping other variable constant, okay? So when you have the model without interaction, you're assuming this effect don't change by the other variable. So keeping other variable constant. Now, this is a little confusing, so it's better to make exponentiate, again, like logistic regression. So we get the exponentiation of all those coefficients using exponential coef of multinom, and that gives you the exponentiated value of those coefficients. Now it's easier to interpret. So basically, for a person with low social economy status and with right a score equal to 0, which is not very possible, but however, the odds of general versus academic is 17 times more than the odds ratio of being general versus academic is equal to this, right? Not odds ratio, again, sorry, let me restate that. The odds of being in general versus academic is 17.3. And the odds of being in vocation versus academic is 18.4, right? So from these, we can get the probability actually of general and vocation if we have all of those, right? So again, if we go back to the part that I put as getting probability from odds, okay? But directly for this value, you cannot get probability. You need both of them, okay? So, but somebody with writing a score is 0 is very unlikely, so it doesn't really helpful to interpret those. However, for example, for this coefficient, that coefficient tells us that for one unit increase of the right score, the odds of being in general versus academic expected to decrease by a factor of this value, by a factor of 0.94. Or if you want to get in the percentage, is on average, it decreases by 6%. For every unit increase of right score, keeping social economy status constant, the odds of being in general program versus academic decreases by 6%. So that's how we interpret this. This one, again, is for 1 unit increase in the writing score. The odds of being in vocation versus academic decreases by a factor of 0.8926, right? That's how you report the results. Now, another coefficient was this one, right? This value, odds of this one, right? This one. So the odds of being in general program versus academic program expected to decrease. No. This is not that. Expected to decrease, yes, this by a factor of 0.3126, switching from low to high. Social economy is from low to high. So if you want to compare a person from social economy low to high, keeping their writing score the same, the odds of being in program versus academic program is less by a factor of 0.31. Very confusing, I know, but this is how it is, the multinomial logistic regression. Another one was this one, right? Now, I want to compare middle to low social economy status, keeping right as constant, and see what happened to the odds of general program versus academic. So the odds of general program versus academic decreases by 41% about switching from low to middle, right? And also you can interpret these odds. The other one, this one is 3.7, this one. So this is the odds of vocation versus, excuse me, versus academy when you switch from low to high. So social economy status switching from low to high decreases the odds of vocation versus academic. Excuse me again. So now, if you want to get the test statistics for all these coefficients, we can, excuse me, we can calculate the z-value by dividing the coefficient divided by their standard error. After doing that, you get the z-value, and you can approximate the p-value by using the tail of normal distribution. So we get the high upper tail of the absolute value of z. So if z is negative, you get the upper tail, and times 2, 1 minus that 2 tail, it gives you the p-value for two-sided test statistics. So this is basically testing whether or not that coefficient is equal to 0. If we do that, we can print z and the p-value this way. So you get the p-value for each of the coefficient, whether or not equal to 0. You can see the right has the very small p-value, which means it's highly significant, and also for this one, and so on, so forth. But now, if I want in general to see if social economy status has effects on people picking some program in their school, so basically I want to test overall effect of social economy status on the variable program, then I have to test all these four at the same time to be equal to 0 simultaneously. To do that, I'm going to use likelihood ratio test. So basically, I run the model with restricted this coefficient equal to 0 and test versus the full model or less restricted model. So basically what I do, I run the model updating. So update is also a function that you can use for any type of model usually. So I'm using for this model. I update the formula by this. So this way I exclude social, or you can run the model again, this time without social economy status. It doesn't matter. And then keep the result as .r. For me, I wanted to restricted model, so I put .r for that model. And if you run that, it runs the model again, right? And it gives you the converged model. And now I can do likelihood ratio test using ANOVA. So this is the restricted model. This is the full model or less restricted model. If I do that, then I get the result of likelihood ratio. So basically, this is the degrees of freedom of the restricted model, right? This is the degrees of freedom. This is residual degrees of freedom, not degrees of freedom of the model. The difference of degrees of freedom is here. This is the residual degrees of freedom, right? The model degrees of freedom is 4. So, and here the model degrees of, but the difference between these two degrees of freedom is how many parameters I set to 0. 1, 2, 3, 4, right? So, and that gives me likelihood ratio, which assumed to have a chi-square distribution with approximately or asymptotically with 4 degrees of freedom. And this is the p-value of that test. So basically we can write it this way. So we can say chi-square is equal to this with 4 degrees of freedom with this reject at alpha 0.05, indicating that based on our data, the effect of variable social economy status on program controlling for writing score is unlikely to be by chance, right? So you cannot omit social effect of social economy status on the program. So now, again, however we try to interpret the result, it's hard to understand that result of is a good idea to get the predicted probability for different level of outcome, for different level of predictors also. So we can get the fitted. This is basically predicted probability for observed data based on the model. So based on each row of the model, each writing every student, this is the predicted probability. So it's probability of being in academy, being in general, being in vocation. They adds to 1, right? Now, let's say we want to, this is helpful, to get the predicted probability of the different level of social economy status for if a person has the average writing score. So that gives us a good idea about the result of the model, right? So in order to do that, we create a new data set that has social economy status in different levels that it should be, or all the levels. I can, instead of this, I can say levels of HSB $ social economy status, SES, or I just type it here. And then their variable right at mean, right? So this data frame is basically, if I combined with the predicted, this data frame is basically social economy status low, middle, high for value right at equal to their mean. So this is the mean writing score, right? If I do that, if I get the predicted probability using predict function and this new data and the type of the prediction to be probabilities. So probs is the type of this predicted probability, is giving me the predicted probability for each of those levels. So probability of academy, general, and vocation. And you can see as social economy from low go to high, predicted probability of academy for an average writing score goes higher, right? Predicted probability of general, so more likely people go to academy with higher social economy status. So on and so forth. You can see, now you can get the idea about how is actually good, what is going on in. So another way is to get the average over everybody's writing score and get the predicted probability of the outcome for each of those social economy status, right? So basically, I want to calculate the expected predicted probability, right, for average writing score for each of those level of low and middle and high. To do that, again, I create a data set that has low, middle, and high. But first, I go from lower writing. So writing score is range between 31 and 67, right? So I go from 30 to 70, which is 41 value of right. And then I want that 41 value to be repeated for social economy status low, medium, and high. So if I run that, then I get the predicted probability. And then again, I see binded with the new data itself, so I can see the data, and this is the predicted probabilities. So this is for low writing score from 30 to 70, and then from middle writing score 30 to 70, and then for high writing score from 30 to 70. This part that I create new data is very useful. So for any type of model, if you want to get the predicted value, it's a good idea to really understand how you create a new data in R. So this is basically how we can do the marginal outcome, right? Or marginal prediction. Then I can calculate by each social and economy status average of these predicted probabilities. Okay, so this is basically average predicted probability. So let's say for everybody in social economy status high, on average, the predicted probability of going to academic general education is this. Now, the average is going to be this when the social economy status is low, and is going to be when the social economy status is medium. I don't know why this comes. Oh, because when I do that, it goes low, middle, and high. Oh, by I see. Okay. And then if I do that, when I do by, it's already automatically do that based on the order of these names. So as you see that again, the going to academic when it's high is higher, the probability going to academic is higher than when is low and middle, right? I'm going to use the same data set to plot this outcome, predicted probability. Basically, I want to see how the predicted probability change from different value of right. To do that, I need to make the data in the long format. So if you see now this data, you have academic, general, and vocation in 3 columns. I want to create 1 column of the predicted probability and 1 column that tells me different level of the same thing as the database of the academic as program, one variable of program which has 3 different levels. To do that, I need to reshape the data in the long format. To make the data in long format, I use this tidyr package. You can use reshape2 package. There is a many way to, but this is more recent. I like that. It's very easy to use. So basically, I tell which columns is going to be in long format, and then I can tell what should be the name of these, and then what would be the values. So it put the values in the probability, and it tell me what is those probabilities, basically the names. So then, and then it repeats everything else. So it doesn't care about those. It repeats those. So basically, the first row is going to be these, and then academic going to be the name. And then the second row is going to be low, right, 30. This is probability, and then academic to be general, and so on and so forth. So if I do that, I get this type of data, which is a table. It's kind of data frame. It's tidy data. So I have this social economy status, this writing scores, and so you see for each row, I have 3 rows. The program and the probability for each of those. All those probability is going to be in 1 column. Then it's easy to plot it using ggplot. The whole idea was to plot it using ggplot. That's why I made it a long data. So I can use ggplot and ggline to plot, write probability as prediction of different value of right. And then I can split it by social economy status, and I can split it again by academic, general, and vocational. So different color means different social economy status, and different facet grid is going to be each of those programs. So that's how I can do the facet grid program. So you can see this is a good explanation of how the data behave. So basically, it shows that for the probability of academic is increases as writing score increases, right? And it increases this way for different level of high. And then if you compare this red to this one and this one, so this is for social economy status high. So if probability of academic increases, these 2 probability will decrease, right? So that's for the plot. Now I can use package Logit, which is another package to run this. I go through this very fast. Again, I said it's easier to use NNet. It's not the best way. Package Logit, mlogit, is multinomial logistic specific for multinomial logistic. However, is a little harder to understand it because it has a special data structure, but it has more into it. So you can run mix effect multinomial logistic regression, for example. I'm going to do that quickly here using this package. I have to reshape the data. I have to make the data as mlogit data, which is index data frame format. And it depends on how your data, structure of your data is. It could be more complicated than this. But in our data, because we have one variable program, that variable goes to that choice part, and the shape is going to be wide. But however, is make the data in long format. So if you look at the data before, now you can see that for every row of the data, we have 3 rows. And then we have this program as false, false, because that program was true, right? Okay, true. And then you have that alternative. So it was, in fact, vocation. So the first row was vocation, but it makes it this way and tells you what type of alternative. This is good for choice data when you have people choose different category or they rank those categories. So it can expand this multinomial logistic. By itself, that package could be 1 or 2 workshops. So there is a lots of things that we cannot cover. But however, I show you how you can run this model. The good thing is that if you run this model, and you have to be very specific in the model. So it's programmed ~0, and there is pi. And then you put the variable, the predictors here. So you run the model like this, you get the result of the model. This called in their package mlogit. It calls pure multinomial logistic. There is other method that you can run. So, however, you run this, you get the summary, and the summary result again is the same thing. It gives you the same summary result. Then you get the intercept for each of that level versus reference level. And then you get all the coefficient. But you get in the column wise, right? The good thing, these 2 parts is exactly identical from a multinom function from NNet, but in addition, you get the z-value and p-value. So I don't have much more for this package for you, but again, it's not very easy to run this multinomial using this package. So there are good resources, and there are some papers based on this package. You can search in R and then get those variants of this package, which is helpful. So for now, we are going to do exercise. We're going to a quick break of like 10 minutes. And then we come back for ordinal logistic regression. For an exercise, you can use that R code in the website. We are going to use HSV data. I ask you to make the math as centered math, because remember we said there is no math score 0. And we want to run multinomial logistic regression with social economy status variable as nominal outcome. So it's not ordered again. That's why I didn't order that variable at the beginning. And use CMAT and female as predictor. And I add CMAT and female as interaction part. So I can do it, you can use it this way, or you can just put a star between. So there's result is here, but don't look at that. I'm going to put back this exercise here. So try to run the model by yourself. Okay? And you can start a break and come back at 3:12. How about that? Is that okay? And then meanwhile, I can also answer the questions. You can unmute yourself and ask questions if you like to. Okay, here is. Yeah, there are other packages. You know, there are about 10,000 packages in R. So some of those packages I don't know, but I find that mlogit package helpful. There is a lots of things in this. Oh, I see. This is Bayesian logit, Bayesian logit, multinomial Bayesian logit. I don't know. Right. Mix effect. Yeah, you can do that. Okay. We are going to continue running this example. So this exercise too. So I made the math using a scale as center is true and then a scale as false, which is a standard error. I don't scale it based on a standard error equal to 1. So then the mean is going to be 0, right? And then I can run the result. Let me so basically I put that result from copy paste it here for you. So I use multinom, math and female, and then I add interaction between math and female. Or again, I could take this off and just put a star here to include interaction. You can run this and then get the result. As you see, for each of those coefficients, this is the coefficient for interaction. You get one estimation. And I can use the choice model. Remember, I created this math, CMAT, so I need to reshape it again. Or I can add this CMAT, but it's easier to reshape it after I made the CMAT in the data. So now I include a CMAT in the data itself, so I can reshape it and then run and logic and run to get the result with the p-value stuff. So that's it. And I don't think we have time to go over this explaining the coefficient, things like that, but it's going to be the same. The best is to create the exponentiate those coefficients and then interpret those, or you can plot them. So then you can create the math and create the female. Especially here you have interaction, you can see how the effect of math change for female. So we don't have much time for that, so I just leave that here and going back to the workshop. So the next model is ordinal. So when we have ordered categorical random variable. Now, again, here I need to define some sort of odds, right? But in a specific way. In ordinal logistics model, or sometimes called cumulative link model or logit model, we use a cumulative odd instead of odds. So what I mean, I define this new odd or cumulative or general definition of odd as odds of being smaller than a category from a small j from 1 to capital J minus 1. So capital J minus 1 is the highest order category. So because it's ordered, right? You cannot just change the reference group. You have to decide where is your highest and what are the low from high, right? So J1, a small j equal to 1 is lowest order. And then 2 is the next order. And then 3 is the next order. Up to capital J, which is the highest order. So if you order it like that, then probability of outcome being less than jth, a small jth order, is equal to probability of less than jth order divided by probability of bigger than j. This is actual odds, right? But it's kind of like cumulative. It's not odds of one level versus other one. So this is one probability divided by 1 minus that probability, right? Because if you add these two, you either less than a small j or bigger than a small j. However, we don't have probability of y bigger than capital J is 0, right? So we cannot define this odds for the highest level, right? So because then it's going to be something divided by 0, which is infinity, right? Okay. So now we model the cumulative odd model or ordinal logistic regression model. It defined as log of logit of this probability, right? Or log of probability of y less than a small j or the group jth, right? J from 1 to capital J minus 1 again, given predictors divided by probability of y bigger than that level, right? Or 1 minus this probability. That is equal to linear prediction again, right? So this is how we can define this probability, and we can link this probability to a real number, which is between negative infinity and infinity. And that's the idea. That's basically what we want to do. So as you see, for every jth level, I define this model, right? But however, if we can make assumption that the effect of each of those predictors are equal for every level, a small j, then we can set all these to be constant for every small j, for every level. We call these proportional odds assumption, right? So basically the proportional odds assumption is the effect of predictor on the cumulative odd is constant. That's what proportional odds assumption is. Okay. So, and then there are tests for that assumption. Basically, in this workshop, older time, people were using package mass and use function POLR. But I'm going to use ordinal package, which again is specific for this, is the newer package and is very good actually. And use function cumulative link model or CLM. And if you look at the help file of CLM, you can see the setup of the formula. There is like formula, there is a scale, there is nominal that you use later, and there is beta, there is weight for each of those observations and more. There is a lot more, okay? So I'm not going to go over all of those. And there is different kind of link. You can see that there is probit link. You don't have to run the model based on logit. You can run it based on probit. Probit is another link that link this probability to this linear predictor. Okay, so basically this link is how you link these two, what kind of function. Okay, so there is cumulative log, and stuff like that. And honestly, if you ask me what is the difference, why we use this and not this, I know a little. So I know that using probit is better when there is no proportional odds assumption. But again, it's not perfect. It's not, still you have proportional odds assumption, but it's more robust, something like that, right? So if there is no proportional odds assumption, they use probit. But if there is no at all proportional odds, you can relax it and run this model actually. And we will do that. And I show you how to do it. So again, but you have to, estimate more coefficients, and it's not always ideal to estimate lots of coefficients. So one more thing, when we run this model, somehow in some of the statistical packages, like or in other programs, or for example in POLR of mass, and also here by default, it gives you minus of those betas. It doesn't give you betas as coefficient. It gives you the coefficient, it gives you these etas, which are negative beta. So basically run the model based on this model, right? Okay, so be careful. But some packages not. So, in other packages, this value is negative, the threshold, and this intercept, but these are positive. So in R, in this example, I'm going to run using this logit data from our website, which is the data from whether or not people apply for grad school, given their parent education, whether or not they attend public or private school in their high school or in their undergrad, and what is their GPA, right? So public or private, parent education, and also GPA, that, and then they, whether or not they apply or how likely they apply for a grad school. So this is a survey of 400 students. Is hypothetical data. It's not a actual data. It's just created for this example, for this order logistic regression. So for the first example, we run the model based on apply predicted by parent education. So if we run the data, read the data, and then as usual, we look at the data, you see apply is 0, 1, 2. So 0 for very unlikely, 1 for likely, and 2 for very likely, right? So unlikely, likely, very likely. So that's the order categorical variable. There is parent education. 0 is not attended grad school. 1 is for attended grad school. Public, 0 for private, 1 for public, and there is GPA score from 0 to 4. So first, let's make the data in a way that we can use in order logistic. Some software, they can take this 0, 1, 2, but it's better to make it as a ordered variable. So I make the factor with the label unlikely, somewhat likely, very likely, and order true, right? So you can see that this is ordered with true level, unlikely, somewhat likely, likely, and there is underneath number for each level. So later, if you want to make it as numeric, unlikely is going to be 3, somewhat likely is going to be 2, and then very likely is going to be 1, right? So 3 is basically unlikely. 2 is somewhat likely. 1 is very likely. Yeah. But these numbers are not directly translated from these numbers, right? So this 2 is going to be 3. Yeah. Oh, sorry. One more thing. 3, I think, is the higher order, but I'm not sure. We can check. But anyway, I think the unlikely is going to be 0. 1 is going to be somewhat likely. Yeah. And then very likely is going to be 2. Also, I ordered the factor, the parent education as factor 0, 1, and label it as not attend and attend. So not attend is going to be now 1, and then attend is going to be 2. I use package ordinal. The function I'm using is CLM to run the order logistic. Again, the formula is going to be the same formula as every regression model and the data. If you run that and get the summary, get the order logistic estimation with proportional odd assumption. So as you see, I get the estimate for each level for threshold, that intercept, and then I get the slope for the predictor. So this is the difference of log of odds, right? The change in log of odds if you go for parent education, not attended to attended. So if I write this formula, this result as the formula in 3.3, I get this, like, you remember that I said this gives us the result as negative. So if I want to put it in beta formula, I have to put negative here, right? So that is actually is a key in the ordered logistics, so you have to be careful. So the level small j is 1 and 2, and then 3 is the capital J, right? And again, going back to this data, unlikely is a small j equal to 1, somewhat likely a small j equal to 2, and very likely is capital J equal to 3. Okay, so if I write the model, is going to be like this, right? So then we can get the confidence interval again with confident ordinal, which is default, is the profile confidence interval. And then you can use which is again, I explained it before, that this profile confidence interval is a confidence interval that extracted from likelihood ratio test. So it doesn't assume that the coefficient is symmetric, right? So that's how it is. And then the confidence interval with the default, okay, is not the default. Default is profile, but if you do confidence dot default of the ordinal, gives you confidence interval assuming normality, which is a confidence interval that has basically is a symmetric, is used plus minus 1.96 standard errors, basically. But this one is not symmetric, okay? So you get the confidence intervals, and then we can interpret the result. To interpret the result, I make it as odds ratio. Basically, I exponentiate it. Now, you have to be careful a little. Now I exponentiate it. Remember, if I exponentiate the coefficient itself, right, I get the odds ratio, right? But that is negative of that value is basically, of that slope, is basically beta coefficient, right? So this is the odds. If I directly take the exponentiate of that coefficient, gives me a reciprocal of that odds ratio. What I mean by that, when we interpret, for example, for a student whose parent did attend college, the odds of being likely versus unlikely, being less likely, sorry, let me restate that. The odds of being less likely, right? So being unlikely versus somewhat likely and very likely directly from the, I interpret directly from beta. To apply is 0.32 times that of a student whose parent did not apply. Remember, the apply did not attend, did not go to college, right? So the reference group was for parent education was not attend, right? So it compares attend versus not attend, and that odds of being unlikely versus somewhat likely and very likely. So basically, these unlikely is a small j equal to 1, less than equal, probability of less than equal to 1 divided by probability of bigger than 1, right? So that's the odd. Now, however, I add this inverse, this one, which is actually the negative one, right? So exponentiate of that negative of beta gives me this. So now I can explain, instead of unlikely versus somewhat likely and very likely, I can compare unlikely and somewhat likely versus very likely, but in the other order, right? Because this is 1 divided by odds ratio. So then I can say for a student whose parents attend college, the odds of being more likely to apply versus versus unlikely and somewhat likely, right? So odds of being very likely versus somewhat likely and unlikely is 3 times more than a student whose parent did not go to college, right? So I know it's confusing, but you have to be careful by that negative positive. So I'm going back to this formula one more time. This one, right? So again, if I use, this is the negative beta. So if I exponentiate this directly, then I didn't go for this log odds of less than 1 versus bigger than 1, less than equal to 1, or equal to 1 versus 2 and 3. I actually explain it as 3, 2, 1, and 2, because this is negative, right? This is negative of beta. Now, if I do if I apply the negative to this coefficient and then get the exponentiate, I get the direct this formula. So I have to directly interpret as less than this, 2 bigger than this, less than equal to this level, 2 bigger than this level. And because of the proportional odds, these two values are the same, right? So it doesn't matter, I say less than equal to 2, which is 1 and 2 versus 3, or I can interpret it as less than equal to 1, which is 1 versus 2 and 3, because the effect in these two are the same. Make sense? Hopefully. Right. So let's move on, and then if you have questions, then I can answer to you. Let's actually we run this model with more predictors, and then we can discuss that more. I can use package mass and POLR. I get the summary. You see, again, it doesn't give us somehow, doesn't give p-value because the author of this package didn't like p-value, maybe. And then most likely they like the likelihood ratio test. So And then you can calculate the p-value yourself by using that lower tail of false of absolute, like upper tail, right? So I did that. And then multiply by 2 gives you that whether or not this coefficient equal to 0. So I get the p-values here, very significant, all of them, right? Usually we don't interpret those intercepts. So we said we make the assumption of proportional odds assumption, right? In order to test proportional assumption, I'm going to use likelihood ratio test where I compare the method to my model, which restricted this coefficient to be equal for 2 equations, right? To the model that I relax that assumption and I make the model to be able to estimate the coefficient for each level compared to other level bigger than that, right? So each level less than each level to bigger than that level, less than equal to each level to bigger than that level, right? So the good thing about the package mass cannot do that. So I'm going to use package ordinal and CLM. Now I can relax this parent education proportional up. So I can make nominal equal to this. So this option is a formula here. So you put tilde before all the predictors that you want to relax proportional odd assumption. And then you put 1 here. So it's intercept only. Because I want to put every variable relax. If I have multiple variable, I want to keep some of them and assume proportional odd assumption, I can put them here. And the one that I don't assume proportional odd assumption in nominal, right? So run the model as nominal outcome, basically, not ordinal. So if I run this model, I get, as you see, coefficient for everything, right? So I get 2 intercept, also 2 parent education attempt, right? So the purpose of this wasn't to interpret that, was to test the likelihood ratio. So I can use ANOVA function again, unrestricted model versus the restricted model. So this is the full model basically, but it doesn't matter which one comes first. You run this, and then this is the model that I relaxed. And then I get the ordinal logistic for the model that I restricted and for the one that is unrestricted or is relaxed. So it estimates each of those separately. And then I get this likelihood ratio stat, and this is the p-value. So that means it's appropriate to use that proportional odds assumption, right? Making that unrestricted doesn't do any good, basically, right? Doesn't improve the model much. So is okay to use proportional odds assumption. There is a package branch somebody wrote that can use on the polar POLR from mass function only. So it's like wanted to complete this mass package that can give you proportional odds assumption using Brandt test. Brandt is the, is a paper published in 90s, I think, that they actually propose this type of test, which is not likelihood ratio. I think it's based on kind of wall test. So if I run this, you can see because there is only one predictor, it tests for every predictor whether or not they have proportional odds assumption. And as you see, degrees the degrees of freedom 1, because it's only 1 here, is the same. We use the chi-square statistics again, and the chi-square value is here 0.02. Here we had very close, right? Very close. And these two are close. So basically very consistent. These two methods gives us very consistent results. Another thing, these tests are very conservative. So there might be proportional odds and the test reject. So, and you know, in literature, people say violating proportional odds assumption is not really a big deal unless you're violating that assumption greatly. So we did that test of proportional, and now let's run together the model that use apply and parent education and public and GPA as predictors. Okay, ready for that? Let's go to R and then run it together. So I give you some time and then I ask some questions and answer some questions, and then we come back to this model. Okay. Any question, anybody? So it's 3:47. We have about 10 minutes to finish this exercise together. There is another part that I plot the data, so let's do it. Okay, so I'll read the data. So this is the data, right? So, and then I have to change the apply to unlikely, somewhat likely, and more likely. Let me see. Yeah, $sign. Actually, so it's unlikely, someone likely, very likely. And then if I get the heads of very likely. So very likely was 3. So basically this, what you see here is not order, is the way that the data is, right? So very likely was first observation, then second observation, and the third observation, right? But if I do str apply, right, is going to show me this. Okay. But these numbers are not really important. The important part is in the data, you see number 2, the value before I change it to factor was 2, and then this was 1, and this was 0. So I make parent education factor. I get the levels of parent education. I change the label, and then this is the label. And so we did, okay. So another thing is, because we are going to use public and private, I'm going to use this at public and private. Okay. So this is exercise. So I'm going to keep this part here. So the model, I'm calling the model. Let me call the model the way that I called it in here, because later I want to use that to plot it. So I call it MCLM. So MCLM is CLM, and then I have apply. It is modeled as, so it gives you the options, right? But we are not done with the formula. So is parent education plus public plus GPA, comma, data, or to that, right? So we can read the model. So summary of the, so you see, I don't have to say ordered or anything else, because this is cumulative link model. So m.cln, I can run it and get the result, right? And then I can, so this is the estimated value, but this is the log of odd metric, right? So I can get the coefficient. So this of the summary. This is one way you can just already get the coefficient directly from the model itself. M.cln. And then I get the estimated, all the coefficient. I could do m.cln. Actually, I can do confidence as confidence interval, right? So that gives me the confidence interval. But you can see this is based on profile confidence interval. So basically, I wanted to get these estimates. So I don't interpret the intercept, I interpret these. So I do get exp of coef summary, and then 1, 2, 3. So 1, 2, 3, 4. So 3, 4, 5. 3, 2, 5, and 1. So I don't want to include this one. I can actually, but yeah. And then I can get the confidence interval too, because maybe you know, if you want to get the confidence interval of log odds, it's always better to use the exponentiate of confidence interval. So let me call this CI. And then cbind this with CI. So I get the exponentiated confidence intervals and exponentiated of estimates. So now let's interpret this one. So this is basically the outcome was apply. So the odds of unlikely, so if I Okay, if I do negative of these, I get the inverse of this value. But when I want to directly interpret these, I have to go from the highest level to the other level. So the odds of very likely versus unlikely and somewhat likely is going to be is changed by a factor of 2.85 for parent education switching from not attend to attend. And also for public, so switching from private to public, the odds of very likely to somewhat likely and unlikely changes by a factor of 0.94 or decreases by 6%, right? So we can write it. And then for GPA, for every 1 unit increase of the GPA, the odds of very likely compared to somewhat likely and unlikely is going to be 85% more, keeping other variable constant, right? So keep that in mind. Make sense? So it's more likely people apply when GPA score goes higher. So that's what it is, right? So, okay, let's go back to our slides. So basically I ran these models, I get the result here, you can see, and then you can see the interpreting the result here. So I interpret, did my odds ratio was the same? Public parent education attend. I'm not sure, hopefully, but yeah, we can go back and
it was different because you didn't invert, right?
Right. This is this. Oh, okay. I get the same thing, right? This is the same thing using exactly. Thank you. Right. So if you want to interpret these, then you have to go from very likely to less likely. So you have to go from upper order and compare it to lower orders, right? The odds is going to be probability of higher order to lower order. If you want to interpret the exponentiate of the coefficient directly. If you do minus coefficient, which is the actual betas, then you have to use the formula that we use from a smaller to higher, right? So what's that? Here, for a smaller compared to higher, right? Okay, thank you. So you is a little confusing, these ordinal, but and then I actually run this example using proportional odds assumption, and then compared to relaxing proportional odds here. Yes. So with the proportional odds assumption, you see that I put all the variables in nominal, but I could keep, for example, parent education, because I already know parent education is not violating proportional odds assumption. So I could just check it for public and GPA. But after you do that, you get the likelihood ratio test, still I don't reject. So I can keep everything using proportional odds assumption, all the predictors. And then you can run the brands. But if you want to run the brand, first you need to run it using POLR. So after you run it using POLR and running the brand from the brand package, brand gives you for each of those one chi-square and test statistics and p-value. So you see public is kind of like in the, but again, I said this test is very conservative. So, but overall, it gives you this. So if you assume all of them together, because again, you see, this is there is a problem of multiple comparison in our favor. That's the first time I see that multiple comparison is in our favor. So yeah. So you see that for another thing that multiple comparison is in our favor is when you test whether or not a point is outlier. So that's also another place you see that. So anyways, I did that. Just make sure that going in order. Now I want to plot this again. I create the, oh, sorry, we are almost done. We are 4:01, so we just cut. So I'm using the same data, the same way that I created the data in multinomial. I have different level of parent education and public, and then this GPA goes from 1.9 to 400 out, right? And 4 times, so I get 400 data points. And then this is the new data. You don't have to have like 400 anyways. And then I get the head of the data. It's like that, right? So you have parent education, public, GPA, and then you get the predicted probability for each level using this cumulative link model. And again, I have to make it a long format as a one column. And after that, you can plot the model and split it by, I split it by 2 things. One, by different color that I use, whether or not they are applied to 3 different outcome level, right? But also because I have 2 different type of the categorical predictor, so I do facet grid. So in 2 sides, so it's going to be row and column. So there you go. So this is a plot of how the predicted probability of apply changes by GPA in different conditions. Okay, so thank you to bear with me for this workshop. I know it was a little long and lots of very confusing data analysis, which is like when you want to interpret those results, it's going to be confusing. But anyways, thank you for attending the workshop. If you have any question, you can ask. Otherwise, I'm going to wait here a little bit so you can ask questions. So any question? Thanks for coming. I see there some people ask about interactions. We didn't have much time, honestly, to go over interaction in this type of model, but in any regression model, interaction, in model with interaction, you allow the effect of each coefficient or a slope change for the other moderator variable change their level or their value, right? So these models without interaction basically restrict interaction equal to 0. You can see it this way. The only thing is that we didn't cover here. I had some other part that I knew that we don't have time, but the interaction when you want to interpret those and then you want to get the simple effect, the effect in exponentiate of log odd is going to be multiplicative. So it changes the exponentiate because in the odds metric, basically because you exponentiate, then it's going to be this many times of the main effect, actually. So yeah, I see. Those are more complicated model, like mixed effect, logistic. Hopefully we can do some advanced kind of multinomial model, so we can add like choice model and mixed effect. Those are very specific kind of model. I don't know is how many people are interested in those models.
Yeah, I don't know either.
Yeah.
We don't have a lot of experience with those choice models either. That's
That's true. Yeah, we need